Okay, let's continue on limits and their properties. And this section 2.3, we'll talk about continuity and one-sided limit. Okay, we're going to go over how to determine continuity at a point and continuity on open intervals. Determine one-sided limits and continuity on a closed interval. Use properties of continuity. Understand and use the intermediate value theorem. Okay, so let's first of all take a look at three different type of discontinuous scenarios. First of all, discontinuous or continuous is the same thing as discontinuous. Okay, so first scenario is we have a open interval AB, and that's a hole for this part of a curve. So at this point, f of c is not defined. That means it's discontinuous or not continuous at x equals c. Okay, second scenario is we have so this is a case where we have a hole here. The second scenario is it's continuous on interval a to c, right? Its area is continuous within the interval from c to b. Okay. However, that's a jump here. This is what they call it. A gap. Okay, that's a gap here, so that's why at x equals c is discontinuous or not continuous. The third case will be there's a jump here between the solid point and a hole, so this is what they call jump. When you have this, either one of these case, and we know that the function is not continuous at x equals c at that point. Okay, so in order to qualify to be a continuous function, a continuous graph, first one, no hole, no gap. Third one will be no jump. And this is very typical example for all three different scenarios. In this case, other than x equals c, in an interval AB, the graph of f is continuous and uninterrupted. Okay. So it appears that continuity at x equals c could be destroyed by any one of the following conditions. First condition, the function is not defined at x equals c. Second condition, the limit of f of x does not exist at x equals c. And the third scenario is the limit of f of x exists at x equals c, but it is not equal to f of c. So this is a hole, this is the gap, and that last one is a jump. Okay. If none of the three conditions above is true, then the function is called continuous at a c, at x equals c, to be exact. As indicated in the following important definition. Continuity at a point, a function f of x is continuous at a c if the following three conditions are met. First of all is f of c is defined, meaning there's a solid point there on a graph. and limit of f of x when x approaches c exists, that will guarantee there's no jump. The last one is the limit of when x approaches c for f of x is the same thing as f of c, and that will guarantee there's no gap. So continuity is on an open interval. A function is continuous on an open interval AB if it is continuous at each point in the interval. A function that is continuous on the entire real line, negative infinity to infinity, is continuous everywhere. Continuous. It's continuous everywhere, which is the best case. Consider an open interval I that contains a real number c. If a function f is defined on the interval, except possibly at c, and then f is not continuous at c, then f is said to have a discontinuity at c. Discontinuities fall into two categories. First one is called removable. Second one is called non-removable. So discontinuity turn into two categories: removable and non-removable. A discontinuity at C is called removable if f could be made continuous by appropriately redefining f of c. Okay. So let's take a look at three different cases. And let's take a look at the first one. First one is what we know by removable discontinuity. So we basically can redefine this point, fill the hole, right? And then make it a continuous function. Redefine at f of c. Okay. And the second case is non-removable discontinuity, because there's a big gap. So we can never close the gap. Not able to close the gap. And we could not define f of c. The third one is a removable discontinuity, because we can remove this point and fill the hole, right? Remove this to fill the hole. So in that case, we redefine the point. Okay. So those are three popular discontinuity with different treatment. Okay, so let's discuss the continuity of each functions. The first one is rational function. We know that domain is x is not equal to 0. If x equals 0, then that's a discontinuity, right? And within the domain, it's continuous everywhere, right? And second one, x cannot be equal to 1. It's still a rational function, and x cannot be equal to 1. And within its domain, it's continuous everywhere. And h of x equals to, this is a typical piecewise function. Two pieces. First piece is linear equation. Second piece is quadratic equation, separated with different domain. And the third one is y equals to sine x. And this is a typical case, it's continuous everywhere. meaning from negative infinity to positive infinity, it's all continuous, right? So let's take a look at some analysis about each one of the. So right here at x equals 0 here, this function has a non-removable discontinuity. So you can see there's a big gap here. You can never close this gap. Right, this gap. So that's why we have a non-removable discontinuity at x equals 0. All right. In other words, there's no way to redefine f of 0 so as to make the function continuous at x equals 0. Second case, domain of g of x is all real numbers except x equals to 1. So as you can see, g is continuous at every value in its domain. Let's take a look at the graph. There's a hole here, but however, we can redefine that. Right, we can basically factor numerator. In that case, we can cancel x minus 1. So we redefine the function as h of x equals to x plus 1. Now this function definitely is continuous. So this is a typical removable discontinuity at x equals to 1. Okay. And g1 is defined as 2. Newly defined function is continuous for all real numbers for h of x equals to x plus 1. It's a polynomial function, so it's continuous everywhere after we redefine the function. Let's look at the third example, which is piecewise function. As you can see, this is actually continuous everywhere because there's no gap, no hole, no jump, no hole, no gap, no jump. That's why we know that it's continuous everywhere on the entire real line. And it's continuous everywhere. Okay. And for the example, the domain of y is all real numbers, so it's continuous everywhere, right? Some function is a continuous function and it's continuous everywhere within all the real number. Okay, next step, let's take a look at it. One-sided limit and a continuity on a closed interval. To understand the continuity on a closed interval, you first need to look at a different type of limit, one-sided limit. Typically, a traditional limit has two sides, right? Left side limit and right side limit. But however, sometimes we have to deal with a function which only have one side limit. So limit from the right means that x approaches c from the right side, right? It's going this way. So the limit denoted as limit x approaches c plus right side. Plus means right side. C plus means right side of C. C minus means left side. left side of C. That's what C minus means. Okay. The limit from left, as we mentioned before, limit when x approaches C from left hand side, C minus, for function f of x equals L. So going from left hand side. Okay, so this is the limit from the left hand side. C minus means left side of C. One-sided limits are used when taking limits of functions involving radicals because of the limitation of the domain, right? Due to the limitation of the domain. For instance, if n is an even integer, then x, the domain for the function x must be greater or equal to 0. So as you can see, you can only go from the 0 on the right hand side, right? Because x must be greater or equal than 0. This is right side of 0. That's why we can only have a right side limit when x approaches 0 on the right hand side for nth root of x. And then it's 0 because we do direct substitution. Just replace x with 0. 0 taking any root of 0 becomes 0. That's why limit equals 0. So let's learn how to find the limit of f of x. When x approaches -2 from right, plus, right means plus. So here we just gotta replace x. We do direct substitution, replace x with -2 square. In that case, we get limit x approaches -2 from the right hand side. So it becomes 4 minus 4 becomes 0. And graphically speaking, right, this function is a half circle. The graph is a half circle. Approaches -2 from the right hand side, go this way. The y value become getting close to 0. Okay, as shown from the graph. So the existence of a limit. This is theorem. Let f be a function that, and then let C and L be real numbers. The limit of f of x as x approaches C is L. If only if left side limit equals L and right side limit equals L. Putting it this way, limit x approaches C minus f of x equals to limit x approaches C plus f of x, and they both equal same thing, equals to L, and that will give us then we say that limit exists at x equals C. Okay, so let's take a look at the definition of continuity on a closed interval. A function f is continuous on a closed interval AB if it is continuous on the open interval AB, and limit when x approaches a from the right hand side for f of x equals f of a, and limit for x approaches b from the left hand side for function f of x equals f of b. And the function is continuous from the right and then continuous from the left b. Right. Continuous from the right at a and continuous from the left at b. It's like this. At this point, this limit exists. This point and limit exists. In that case, we know that it's continuous in the closed interval. Square brackets a comma b square brackets. Let's discuss the discontinuity of f of x equals to 1 square root of 1 minus x squared. The domain of this f is in a closed interval -1 to 1. It's very easy, right? 1 minus x squared must be greater or equal to 0. Then adding x squared from both sides. We cancel that. So then we have 1 greater or equal to x squared. That means x squared less equal to 1. In that case, x must be greater or equal to -1, less equal to 1. Okay. You're solving linear inequality to inequality to find the solution, the domain. And all the points in the open interval -1 to 1, the continuity of f follows the theorems, and let's calculate the limit when x approaches -1 from right hand side for the function square root of 1 minus x squared. So replace x with -1. So we have a limit x approaches -1 plus equals to square root of 0, which is 0, right? And then this equal to f of -1. F of -1 is also 0. So that means continuous from the right. And we also need to calculate limit when x approaches 1 on the left hand side to verify the continuity on the left. So similarly, we replace x with 1. So we get a radical of 0, which is 0. And then f of 1, which is also square root of 1 minus x squared, which is the same thing as 1 minus 1 squared. Minus 1 square, which is radical of 0, which is 0. And we know that limit, that is the same thing as f1. That's why it's continuous from left. And you can conclude that f is continuous on a closed interval from -1 to 1, right? Let's take a look at the properties of continuity. This is very basic properties for continuity. If b is a real number, f and g are continuous at x equals c, then the following functions are also continuous at c. First one is scalar multiple, b times f. Second one is the sum and difference of two functions, f and g. The product is also continuous at x equals c, and quotient f over g, but we're going to make sure gc is not equal to 0. It's also continuous at x equals c. And then following type of function continues at every point in their domain. All the polynomials, right? It's continuous in its domain. Rational functions, radical functions, trigonometric functions. And as you can see, now we know that using the property of a continuity, we know that all these functions also continuous within its domain. If g is a continuous function at x equals c, and f is continuous at a gc, then the composite function given by f of g of x is continuous at c. Let's take a look at the intervals on which each function is continuous. First one is 10 to the tangent x. We know tangent x domain is everything except pi over 2 plus n pi. Right? So in that case, it's continuous everywhere within its domain. For the second one, y f of x equals to sine of x. The domain is x cannot be equal to 0. So it's continuous everywhere within its domain. As you can see, this is a graph for this g of x. And we know that it's continuous everywhere except at 0, right? So it's continuous on the intervals -infinity to 0, which is open interval, and open interval of 0 to a positive infinity. Okay. And when you graph it, you can see this a lot better. The last one, C. We gotta use the squeeze theorem. Since x times sine 1 over x is greater or equal to negative absolute value of x, less or equal to absolute value of x, then we know that when x approaches 0, this is negative 0. This is positive 0. Then it must be 0. Right? That's why we know that limit for x approaches 0 for a function x times 1 sine 1 over x is equal to 0. So h is continuous on an entire line. It's continuous everywhere. It's continuous everywhere. So let's take a look at next theorem is called intermediate value theorem. And the abbreviation is IVT. So for the intermediate value theorem, if function f of x is continuous on a closed interval AB, f(a) cannot be equal to f of b. And k is any number between f of a and f of b, then there's at least one number c in AB, such as f of c equals k. So basically it's like this, right? Let's say we have a interval AB. Okay. And the function look like this. There's a point C here, right? Let's say this is C. C is right here. So this is f of A. That is f of B. We know that f of C, which is right here, actually is between. This is f of C. Since C is between A and B, right? C is greater than A less than B, then f of C is greater than f of B less than f of A. And since f of C equals K, so K is greater than f of B less than f of A. Right, so this is a key feature about the intermediate value theorem. Okay. Intermediate value theorem tells you that at least one number C exists, but does not provide a method for finding C. Such theorem are called existence theorem. Right? Only proof exists such a point, but we don't know how to find it using under this theorem. A proof of theorem is based on property of real numbers called completeness. The intermediate value theorem states that for continuous function f of x, if x takes on all values between a and b, and f of x must takes on all values between f of a and f of b. Suppose that a girl is 5 feet tall and then on her 13th birthday, and then 5 feet 7 inches tall on her 14th birthday. Then for any height that between 5 feet and 5 feet 7 inches, there must have been a time t where her height was exactly, let's say, 5 feet 4 inches. We know that this is continuous, right? Because human growth is continuous and a person's height does not abruptly changes from one value to another. It grows over time, continuously. Okay, so it's pretty much the same concept. So the intermediate value theorem guarantees the existence of at least one number C in a closed interval AB. It could be more than C, right? In this case, let's say this is the interval A, B. As you can see, there are three numbers here. 3C here, C1, C2, C3, all have a f of C equals K. Okay, so at least one. It could be more than one, right? A function that is not continuous does not necessarily exhibit the intermediate value property. For example, the graph of function shown in this is not continuous at this point. So that's why we're going to find a point x equals c corresponds with y value which is equals k. So the intermediate value theorem does not apply. IVT does not apply. For a discontinuous interval. Maybe. And then one of the most important usage of intermediate value theorems is use it to find the real zeros. IVT used to find the real zeros. Specifically, if f is continuous on the closed interval AB and f of A and f of B different sign, meaning one of them is positive, the other one is negative, then there must be guaranteed at least 1 zeros in that closed interval AB. Okay, just like this, right? Let's say we have a function going from this is positive sign and that's negative sign. Then you see that's a 0 here, right? And let's say negative this 2 and negative 2 here, right? Going from and that's real 0 here, okay? This is B, that's A, right? Then f of B is 2, positive. F of A is negative 2, which is negative. Then as you can see from the graph, that's real 0 in between A and B. Okay. So let's use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 in the interval. First of all, we just gotta figure out what is f of 0. F of 0 equals 0 cubed plus 2 times 0 minus 1. It turned out to be negative 1. So that's negative, right? F of 1 equals 1 cubed plus 2 times 1 minus 1, which is 2. And that's positive. So it goes from negative to positive, so that's guaranteed at least 1 0. 1 real 0 in the closed interval from 0 to 1. Okay. Since this third degree polynomial is continuous everywhere within a closed interval 0, 1, f of 0 is negative 1, f of 1 is 2, then we know that there must be a real 0 in between.